Okay, assalamu alaikum and good morning, guys. Welcome back to grade 10 physics by Inspire Teen. So in today's lesson, we're actually going to be doing some chemistry. We're going to be covering the topic of states of matter and kinetic molecular theory. Before we begin, please can you guys confirm that you guys can hear me, see me, and see my screen as well? Okay, cool. Everything seems to be fine. Okay, let's continue, right? So, this is a very theoretical subject. There is quite a bit of theory. So we're going to go through the theory and then hopefully eventually we can get to some questions and take it from there. Okay. So firstly, classification of matter. Okay. So let's have a look at this diagram. Okay. That shows us that all matter, it shows us that all matter is made up of particles whose properties determine the observable characteristics and reactivity. Okay, so basically it tells us the properties of all matter, how they behave. Okay, so we have atoms, okay, which is the smallest unit. Okay, and then the atoms can be converted into molecules or ions. Okay, and together all of those, okay, would refer to what we call as particles. Okay, so whether you have molecules, whether you have atoms, whether you have ions, a group of ions, we refer to those as particles. Okay, and all matter, anything that exists, okay, is made up of those particles. Those particles which stem from atoms, molecules, or ions. Okay, all matter is made up of those. Okay, then when we break down all matter further, all types of matter in this world, we separate it into two different ones. We have pure substances, okay, which we'll go through, as well as mixtures. Okay, we have pure substances as well as mixtures. Okay, so when we break down pure substances even further, pure substances can be separated now into elements and compounds. That's what we deal with in chemistry, actually, right? We deal with elements from the periodic table, and then compounds, which when we combine multiple elements from the periodic table, we deal with these certain compounds. Okay, and then the elements, okay, they can be further separated into their different kinds: metals, metalloids, and non-metals. Okay, when we go through a what do you call it? Periodic table. It's a very important table. We'll see that we have our metals, metalloids, and non-metals. Okay, so just a little diagram explaining how all matter is made up of particles, where the particles stem from. Okay, cool. Let us continue. Let us look at mixed and pure substances. Okay, so mixtures and pure substances. So this is now when we're discussing all types of matter. How do they split into pure substances and mixtures, and what are we looking for exactly? So in a mixture, okay, we're reading the first line. In a mixture, it consists of different particles not chemically joined. Okay. I'm reading all of this. Okay. Mixture consists of different particles not chemically joined, while pure substances, okay, we have of two different kinds, elements and compounds. Now compounds consist of two or more elements chemically bonded, but elements, of course, consist of one type of atom, okay, but it's still a pure substance. Okay, so mixture consists of particles that are not chemically joined. However, the compound consists of two or more elements chemically joined, and the element is just obviously one type of atom. There's no bond forming between them. Let's have a look at the next one. Okay, we have make a difference between mixtures and pure substances. For mixtures, components can be separated into simpler substances by physical means. Okay, so when we think mixture, we think, okay, this is a very casual example, like a salad. Okay, we have multiple different elements, if you will, in a salad, cucumber, lettuce, and they are not chemically joined. Okay, they can be separated by physical means at times. Okay, but now let's look at the comparison on the pure substance end. These components can only be separated into simpler substances by chemical means. Okay, and so compounds, they can be separated, but by chemical means. Okay, and that's the difference between a mixture. Mixture can be separated by physical means. Excuse me. So then we have the next one. Select it. Okay, the smallest sample will reflect, so we're talking about a mixture. The smallest sample will reflect the composition of the mixture. So like a salad, if you take a portion of a salad, it reflects whatever is in the rest of the salad, all right? However, with pure substances, in a compound, components can be separated into simpler substances by chemical means. Oh, sorry, I'm reading the wrong one. Compounds, smallest particles and molecules or ions. Smallest particles are molecules or ions or formula units. And for elements, smallest particles are atoms or molecules. Okay, let's look at the next one and last and final one. Okay, so firstly, for mixtures, there's no fixed ratio between the different particles, okay? But for compounds, there's a fixed ratio between the smallest particles. If we look at an example, they say example, sand in water, there's no fixed ratio to how much sand you're having and how much water and so on. But if we look at a compound like H2O, for example, there is a certain amount of hydrogens for a certain amount of oxygens, okay? And an element, of course, there's no such thing as a ratio because element is just one single atom, one type of atom, right? So in that case, these represent the difference between mixtures and pure substances, right? I think for the most part, it's self-explanatory. Okay, we talk about mixtures, not chemically bonded, can be separated by physical means. Okay, the smallest sample can reflect the composition, and there's no fixed ratio between how you mix them, basically. But for pure substances, if we talk about compounds and elements, okay, they consist of two or more elements chemically bonded. But okay, of course, elements, the ones are slightly different because it's only one element, but it's still pure. Okay. Then also they can be separated by chemical means, and their smallest particles are molecules or ions, and there is definitely a fixed ratio between the particles. Okay, classification. Excuse me. The elements of the periodic table can be classified into three different categories: non-metals, metals, and metalloids. Okay. So the non-metals, an example is sulfur. The metals, an example is copper. The metalloids, an example is silicon. So for non-metals, the example is sulfur, and they are poor electrical conductors. All right, we know this about non-metals. They are insulators, basically, except for graphite. They are poor thermal conductors, except for diamond. They have a dull appearance. They are brittle. They have low melting and boiling points. Sorry, just 1 second. Apologize, I'm back. Let's continue. Okay, so we're discussing non-metals, metals, and metalloids. So we said that, yes, the non-metals, they're insulators. Okay, they're poor thermal conductors, dull appearances, brittle, low melting and boiling points. Okay, non-metals, okay, they can be solid, liquids, or gases at room temperature. Okay, they could be either or. Let's talk about metals. Okay, metals, an example is copper. Now, metals, they are good electrical conductors, good thermal conductors. They are shiny, okay, They are malleable and ductile. Okay, so brittle, they sort of like weak. Okay, they can break easily. Malleable and ductile means that you can. They each have their own specific meaning. Let me Google specifically what each one means. But they basically mean that you can sort of like bend them and whatever. Let's see. Malleable. So specifically malleable is easily influenced, okay, or metal is able to be hammered or pressed into shape without breaking or cracking. And then ductile, okay, ductile is that it is able to be deformed without losing its toughness. Okay, so it's not brittle. If you deform it, if you shape it, it's not going to break. It's going to be able to keep that strength, but you're able to bend it. Okay, so that's malleable and ductile, and I think we can all picture that or imagine that in a metal. It has those properties. Okay, high melting and boiling points, and all metals are solids except for mercury at room temperature, which we know is a liquid. Okay, let's look at metalloids. So metalloids are the sort of in-betweeners. Example, silicon. They are poor electrical conductors, but conductivity increases with an increasing temperature. They have varied thermal conductivity. Some are good, some are bad. They are also shiny. However, they are brittle, and their melting points and boiling points differ vastly, but they are all solids at room temperature. Okay, so just some key important properties of non-metals, metals, and metalloids that we need to know. Let's look at the electrical characteristics. Insulator. Okay, insulator is a material that prevents the flow of charge, which are non-metals, example, plastic or rubber. That's why cables are surrounded in like plasticky rubber, okay? Because they are good insulators, right? They're not going to let that electric charge come out of the actual copper wire inside. Then we have electrical conductors, okay, or conductors. They are materials that allow the flow of charge, example, metals, and example, electrical cables or materials such as copper. Okay, semiconductors, a conductor that can conduct electricity under certain conditions. Example, these are our metalloids. Example, diodes and LEDs, and integrated circuits. Okay, only under certain conditions they can conduct electricity. Let's look at some magnetic properties. So these are all important theoretical aspects that you need to know for this section, right? Ferromagnetic materials can be influenced by a magnet. Okay, so ferromagnetic materials are materials that can be influenced by a magnet. So they're not magnets, but they can be influenced by a magnet. Some examples: soft magnetic materials. They are easily magnetized but lose magnetism easily. Example: iron. Okay, it uses temporary magnets such as electromagnets in metal scrapyards and loudspeakers. Temporary magnets such as. Okay, so soft magnet materials, they are easily magnetized but lose magnetism easily. Hard magnet materials, they are not easily magnetized but retain their magnetism for a long time. Example: cobalt, nickel, steel. Okay, hope that makes sense. Their uses: permanent magnets and compasses. Let's talk about non-magnetic materials. Materials which are not influenced by a magnet and they cannot become magnetized. Other elements including metals such as aluminium, zinc, and copper. These are materials which are not influenced by a magnet. Okay, so again, some important magnetic properties for you guys to know. Classification of matter, we went through this diagram. Okay, let's look at some definitions. Okay, physical properties of materials. We have strength, the ability of a material to resist stress and strain. Thermal conductivity, the ability of a material to conduct heat. Electrical conductivity, the ability of a material to conduct electricity. Brittle means it's hard but likely to break. Malleable, ability to be hammered or pressed into shape without breaking or cracking. Ductile, the ability to stretch into a wire. Magnetic, a material which can be attached or repelled by a magnet. Its domains are aligned. Non-magnetic, its domains are misaligned, and it's a material which is not attracted or repelled by a magnet. Density, the mass per unit volume of a substance. Melting point, the temperature at which we can say solid and liquid are in equilibrium. Melting point, the temperature of a liquid at which its vapor pressure equals to the external atmospheric pressure. Okay, so those are important. Key diagram, cool. Let's look at these. A pure substance is a substance that cannot be separated into simpler components by physical means. Pure substances consisting of only one type of atom, which these are known as our elements, and compounds, these are pure substances consisting of two or more elements chemically bonded into a fixed ratio. Okay, a mixture consists of different particles mixed together but not chemically joined, right? We discussed that. Let's look at some examples of elements, okay, which we said are pure substances consisting of only one atom. So for example, if we take something directly from the periodic table, that is an element. Okay, those are the elements. Let's see. Okay, those are the elements. And an example is argon, mercury, silicon, or gold. A compound, on the other hand, is a pure substance consisting of two or more elements, basically. Now, when we're combining the elements, we're forming compounds. An example is water, which is H2O, carbon dioxide, which is CO2, sodium chloride, which is NaCl. Mixture, it consists of different particles mixed together, but not chemically joined. Okay, we said like a salad. So here they say what? They say milk, air, salt, water. Okay. Homogeneous mixture, okay, it's a mixture of uniform composition and is which all components are in the same, when all components are in the same phase. For example, air, brine, steel. Okay, heterogeneous mixture, a mixture of non-uniform composition and of which the components can be easily identified. Okay, for example, sand and rock mixture, pizza toppings. I think we get the gist of that. Okay, let's move on to one of the most important pages of your life. Names and formulas. Basic concepts. Let's discuss this. All right, let's see what's going on. Yeah. Atoms combine in very specific ratios to form certain compounds. Example, carbon dioxide consists of one carbon and two oxygen atoms. These ratios remain fixed for that compound. The ratio is given by the formula CO2. Okay, and that makes sense. CO2, one carbon and two oxygen. One carbon and two oxygen, right? So these ratios remain 6 for that compound. The ratio is given by that formula, CO2. Now, simple ions are single atoms which carry a charge. They are also called monatomic ions. Okay, so single charge ions. Examples. Let's do some examples. So these ratios remain fixed. So by the way, another example for this. Oops. H2O, okay, there's many examples, right? Fixed formula again. So two hydrogens, one oxygen, all of these compounds, even a complicated one, let's do CH3COOH, for example, right? Whatever the compound is, right? The only reason a compound exists is because of the ratio that they added together. Okay, 3 hydrogens, 2 carbons, 2 oxygens, 1 hydrogen, that's 4 hydrogens in total. And the ratio of them, okay, is the reason it exists. So yes, so then we have simple ions, okay, and each atom in the periodic table has its ionic version. Okay, we have its neutral version and it's also its ionic version. An example of an ion, if you've seen one before, is like the chlorine ion, Cl, which just has a minus. Or if we talk about like polyatomic ions, which are in the next one, actually we'll discuss it there. Now more single ions would be like H positive. Polyatomic ions are groups of atoms bonded together which collectively carry a charge. For example, SO4, 2 minus. Okay, other examples, NH3, or yeah, NH3, 1 minus. So this entire compound is carrying this charge. We are no longer talking about individual atoms, or we are no longer talking about individual ions. Okay, the entire compound is carrying that charge. Which charge? This 2 minus. So for example, the SO4 is carrying 2 minus charge, NH3, the whole thing is carrying a minus charge. Okay, so that's an important concept to understand. It really is. Okay, these ratios remain fixed. Okay, Anything else we can discuss enough for now? Table of common compounds. Okay, these are really important. I know if you're looking at this and you're like, yes, so much, and you're gonna cry and you're gonna die and everything above, but like it's over time, it's really not that bad, right? As long as you know your chemical names, okay, common elements on the periodic table, right? You start off here: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. You can learn a song, whatever you want to do, but you need to know the most common elements, the one we use all the time, the ones we use sometimes, okay? But you need to know them. So let's look at our table of common compounds, okay? So in this case, we're taking the elements on the periodic table, we're combining them, we form compounds, and this is what we have. So I would advise, again, read through these constantly, right? Most of them are like easy to remember because they follow exactly what the formula is. HCl, hydrogen chloride. Okay, NaCl, sodium chloride, NaOH, sodium hydroxide, and so on. Okay, so most of them might be easy to remember, and then they have common names also, which is really nice because they deal with it a lot. Okay, so table of common compounds, very important. Table of common elements, very important. Even more important, table of common cations and anions. Okay, so I want you guys to have a look through this. I just need to go to the bathroom quickly, so just have a look through this question, and we'll come back and we can discuss it. Okay, I'm back. Let's continue, right? So why is this important? Because you see this table of common cations and ions, you'll take this with you till metric, okay? The quicker you learn it, the better, okay? Because once you learn it, okay, you will be able to formulate different compounds, okay? You will be able to know the names of different compounds. You will be able to know in your test, in your questions, which compound are they referring to when they say hydrogen nitrate, when they say sodium hydroxide, when they say hydrogen chlorate, or whichever one, right? You'll be able to know it. And like I said, the quicker you learn it, the better it is. And trust me, most of these are really important and they'll come up and you will need to know them. So what many people do is they leave it out because it's a bit too much. and then it comes back to bite them. Let's just go through what I would say are like the main ones, the most frequent ones. Okay, so look, honestly, all of them are just as important because they could randomly decide, okay, we're going to put that in the test, and then you don't know it. So just learn all of them. But I highlighted for you the ones that are very common, extremely common. You're going to see them all the time, right? But yeah, like I said, the others, they have an equal chance of coming out in a paper or you needing to know them. Okay, so yes, table of cations and anions, and you'll see how we'll work with them when we start naming compounds. Okay, we'll be working with sulfate ion and sulfite and nitrate and nitrite. Okay, we can come back to that when we do. Okay, let's move on to names and formula. Okay, so I think we're a little bit out of the theory now, which is good. This theory is boring, but on the practical end, right? Writing chemical formulae, follow these basic steps to write chemical formulae for ionic, not iconic, ionic substances. Number one, write symbol for the positive ion first, then for the negative ion. The ions could be monoatomic ions or polyatomic ions. Number two, write ionic charges. At the top right of symbols, monoatomic ion, the ion is, okay. Let's not read all of this and torture ourselves. Let's do an example, okay? Then you can read the rules on your own and see if they make sense and if they're going to help you. But let's do it practically so we can understand practically how to name, what is this? Writing a chemical formula of a substance. So if we have aluminium oxide, now aluminium, okay, whenever we formulating compounds, whenever we, what is this saying? Writing the chemical formula of compounds, we need to know its ionic charge. That's important. Its ionic charge. Okay, let me just snag a periodic table quickly. Share my screen again in 1 second. Okay, here we go. I share my screen. Okay, so here we go. Here's a periodic table, right? So we're talking about ionic charges. Now, ionic charges we discussed, we actually get single charges, so elemental charges, if you will, or charges to do with elements. Then we have polyatomic, monoatomic, I guess, but polyatomic, basically compounds. So elemental charges, I'm not going to put the L, just so leave it as element, just so it's less confusing. So the elemental charges are basically the charges, I'll give an example, of like hydrogen plus or just chlorine, one single element and its charge. But polyatomic, okay, that's like that table. If I have like SO4, this whole thing has a charge of 2 minus. That's polyatomic, many atoms, right? So yeah, again, this is why this table is important, especially you have to know their charges as well, positive 2, negative 2, and so on. So the ionic charge, the elemental charge, and the polyatomic charge, we have, okay, so those examples. Now, how do we determine them? Using the periodic table. So how do we determine the elemental charge? So firstly, we determine the elemental charge from the periodic table. How do we do it from the periodic table? We do it as follows. We follow the Roman numerals, kind of, where this has a +1 charge. All of it in that group has a +1 charge. Here they have +2. Then you skip all these metalloids in between. Here you have +3, plus or -4, -3, -2, -1. So yeah, from the Roman numerals ones only, from 1, 2, I believe that is 7. Yeah. So 1, 2, 3 minus plus 4 minus 3 minus 2 minus 1. Okay, so those are the elemental charges, right? They follow the group. You need to know those. Okay. Then where do we get polyatomic ion charges from? There's no way to get it from, unfortunately, except this table. So you have to memorize this table. They're not going to give it to you. They're going to give you the polyatomic ion charge. They're just going to give you it and expect you to know it. So yes, now aluminum is actually from the periodic table. So what charge would it have? We have a positive 3 charge because it's in the third group. It's in the third group, so therefore it has a charge of positive 3. So we jot that down. Oxide, where do we get oxide from? Oxide is oxygen, which has a 2 minus charge, but also if you pay careful attention, you get if you don't pay careful attention because it's not in here. But oxide is O2 minus. Oxygen with 2 minus. Okay, that's its charge. So the one's charge is 3 plus, the other one's charge is 2 minus. What we always do is we cross. Right, let's start off with the second one. So another example, let's do H plus and Cl minus. Okay, so in this case, you cross over each charge. So basically, the charge of chlorine will go to hydrogen, so it's 1, so it stays as 1. The charge of hydrogen will go to chlorine, so it's 1, it stays as 1. So this is just HCl. This is just HCl. Okay, let's look at another example. Yeah, okay, let's do this one. Mg2 plus and Cl minus. Okay, so an atom with a charge of 2 plus and another atom with a charge of 1 minus. So basically we cross it. Okay, what do we mean by cross it? The charge of Mg becomes the subscript of Cl, and the charge of Cl becomes the subscript of Mg. Does that make sense? So basically, this will become Mg. It has like an invisible 1 there, and then Cl2. Cl takes that 2, and then that 1 goes there. Again, it's like an invisible 1. We don't have to write it. We can get rid of it. We can get rid of it, right? MgCl. That's our compound. Let's do another example. Okay, that's fine for now. Now, how would we do this? Okay, simple. The way we do it is we cross as well. The charge of Al becomes a subscript of O. The charge of O becomes a subscript of Al. So this becomes Al. Take the charge from O and make it a subscript, small subscript. The subscript is a little small number, so I make it 2. Thereafter, I take oxygen and I take the 3 from Al and I put it there. Okay, and then exactly what happens if they balance out? So if we have Mg, okay, I'm going to do Mg, for example, Mg and SO4. Mg is 2 plus, and SO4 is 2 minus the whole thing. When we combine these, the 2 and the 2 cancel each other out. So you basically have MgSO4. Okay, so crossing makes sense. So that's how you cross. Let's look at this. It says phases of a compound. Phases are represented as subscripts after the following formulae as follow. S is solid state, L is liquid state, AQ is aqueous solution, G is gaseous state. So S, L, AQ, and G. S, L, AQ, and G. Those are important to remember for your chemical equations. Now let's look at the balancing of chemical equations. A chemical equation represents the chemical changes that occur when a reaction takes place. The law of conservation. The law of conservation of matter means that matter cannot be created nor destroyed. Merely it's transferred from one substance to another. A chemical equation must be balanced in order to perform the above law. Compounds have fixed ratios. Compounds have fixed ratios, thus only the number of compounds on either side of the arrow can be changed. Numbers are placed in front of the compounds on either side of the arrow to balance the equation. The total number of each atom should be the same on either side of the equation. Steps for balancing reactions, equations. Steps for balancing reaction equations. Sorry, 1 second. Sorry about that. My niece was trying to phone me. Okay, so steps for balancing reaction equations. So these steps, let's go through them. Identify all reactants and products of the reaction. Yeah, duh. Start the word equation where possible. Write the correct formula for the compounds of the reactants and separate them with the arrow. Okay, great. Indicate the phase of each compound. Count the number of atoms in each element on either side of the arrow and add numbers in front of the compounds to get it back to get it to balance. Check the total number of atoms of certain element. Okay, that doesn't help us. Examples in the synthesis of water, hydrogen reacts with oxygen to form water. Okay, let's have a look at this one. Let me get off my notes. Okay, so in the synthesis of water, the creation of water, we have hydrogen, which occurs as H2. We have oxygen, which occurs as O2. And then this gives us H2O. Now, how do we know that this is not balanced? Firstly, how do we know that we need to balance it? We know it's not balanced when we check, okay, remember the law of conservation of matter means that matter cannot be created nor destroyed. So if you're going to use up H2 plus O2, okay, to give you H2O, you're going to use up all of it to give you all of H2O. Okay, and what was I getting here? I forget why I was telling you that. But yes, basically keep that in mind, right? Now, what we have to do is we have to identify how many hydrogens we have on each side. So hydrogens on the left, there's 2. Oxygen on the left, there's 2. Hydrogens on the right, there's 2. But oxygens on the left, how many are they? There's 1. So hydrogens are balanced. So this is what needs to happen. Yes, this is why it needs to balance, is because of the law of conservation of matter. Matter cannot be created nor destroyed. So you have to have however many hydrogens you have on the left, you have to have that many hydrogens on the right. Okay, so in this case, we have to balance it out. We have to make sure there's an equal amount of hydrogens on the left and oxygens on the left and hydrogens on the right and oxygens on the right. So in this case, like I said, our hydrogens happen to be balanced, but our oxygens are not balanced. So our oxygens are not balanced on the right-hand side. So the first thing you can try and do is balance those oxygens. How can we balance those oxygens? Because there's 1 oxygen, and how many do I need? I need 2 oxygens. I can multiply this by 2. Okay, now my oxygens are balanced because now I have 2 oxygens. but I also have 4 hydrogens, because now I balanced my oxygen, but now my hydrogens became unbalanced. So those 4 hydrogens, right? There's no other way that I need to balance that oxygen, right? So I need to keep that 2 there. So now, because I have 4 hydrogens on the right, is there a way that I can get 4 on the left? Because if I can get 4 on the left, then it would be balanced. Okay, let's see. Let's have a look on the left hand side. I can see hydrogen is completely on its own, and it has 2 hydrogens. So if I multiply that 2 hydrogen by 2, then I have 4. So now I can see that, oh, okay, I have 4 hydrogens on either side, and I have 2 oxygens on either side. Hence, this equation is balanced. Let's do some more examples. Equations to balance. Let's not look for an extremely difficult one. Let's do some easier ones. Hmm. Okay, let's try this one. Okay, wait, actually. 10 seconds, sorry. Here we go. Okay, so here's another example. Let's work through it. Fe 203 gives us Fe plus O. Okay, this one's a bit too easy, but it's fine. So we can consider now on the left hand side, how many iron do we have? We have 2 iron. On the right hand side, we have 3 oxygens. On this left, on the right hand side, sorry, we have 1 iron and 1 oxygen. So naturally, the way to balance it is if we can multiply the iron on the right by 2, then we have 2 ions, and now the ions are balanced. And if we multiply the oxygen on the right by 3, we have 3 oxygens on the right, and the oxygen's balanced. So that's a bit stupid. It's okay. Okay, yes, let's look at something like this. It's a bit more interesting and challenging. Aluminum plus O2 gives us Al2O3. I'm gonna give you guys like 2 minutes, 2 good minutes to try and solve this one, and then I'll solve it afterwards. So attempt it. 2 minutes later, I will solve it. Okay, let's have a look at it. So let's understand how much of each element we have on either side. On the left-hand side, the aluminium, we have 1. And on the left-hand side, the oxygen, sorry, we have 2. On the right-hand side, aluminum, we have 2. And on the right-hand side, the oxygen, we have 3. Both are unbalanced, okay? But I'm not going to try and balance the aluminium first, because the aluminium, okay, the aluminium, this is one compound, okay, so it's going to affect the aluminium and the oxygen. So I'm going to try and balance my oxygen first. So on the left I have 2 oxygen, and on the right I have 3 oxygen. Okay, a good trick for you to have the same amount and to meet at the same amount is to meet at 6. Okay, meaning basically like the highest common factor between 2 and 3. Okay, so for the oxygen on the left, right, I already have 2. I can multiply it by 3, and now I have 6. For the oxygen on the right, I already have 3. I can multiply it by 2, and I have 6. I hope you guys are getting that logic. So now they're both the same, they're both at 6. Okay, thereafter, I need to balance my aluminiums. So by the way, aluminium went from 2 to 4. And that's easy now, because aluminium is on its own on the left-hand side. I can easily multiply it by 4, and that changes to 4. So you must always be aware of the ones that are alone, because then you can leave that for last and then sort it out at the end. Because it's alone, you can do whatever, you can multiply it by whatever you want. But yeah, that's how we do this one. Okay, we come back next week. Let's end a bit early, 1.5 minutes early. Kind of like that. It's the holidays, so you know. Okay, so yeah, we'll do like maybe some combustion reactions and some more difficult examples, but these are relatively decent for now, right? Decent examples, decently hard examples. So yeah, okay, all the best for you guys week. I hope you guys have a good holiday, and I will see you guys same time next week, inshallah. Thank you guys so much.